Hey everyone, and welcome to this explainer. Today, we are diving into the incredibly elegant mathematical system we use for unknown quantities. We're going to take a closer look at how simple placeholders can literally save our logic when a crucial piece of data is just missing. Let's jump right in. Here's our roadmap for today. We'll start with what are unknown quantities, move on to math with letters, then translating words to algebra, and finally wrap up with solving real-world problems. All right, section 1. What exactly are unknown quantities? So here's the big question we really need to answer. How do we write a number down when we actually don't know its value? Have you ever wondered what mathematicians do when they hit an unknown quantity? I mean, instead of just leaving a huge, confusing blank space on the paper, they've actually developed a highly specific and, honestly, incredibly elegant system for this. And that elegant solution? It's the variable. A variable is simply a letter. You know, like n, x, y, or z, used to represent that unknown quantity. Mathematicians use these letters to act as rock-solid placeholders for everyday objects or amounts. They essentially hold the space, keeping the whole mathematical sentence logically intact, at least until we can gather enough info to figure out the exact number. Moving right along, section 2, math with letters. Picture this. You have a glass of juice sitting on the table. We don't know exactly how many milliliters are in there, right? So let's just say one glass contains an unknown n milliliters. Now, step 2. Imagine 3 more identical glasses are placed right next to it. We've got 4 glasses total now. Instead of counting every single time or, getting totally overwhelmed by the unknowns, we just add them up. N plus n plus n plus n. And that elegantly simplifies down to our total amount of juice, which is simply 4n. And this logic, it extends super easily to multiplication and division too. Let's say we have 5 bags of oranges, and each bag contains an unknown amount, O. The total is just 5 multiplied by O, which we neatly write as 5O. Pretty simple, right? And for division, imagine a piece of ribbon that is r centiliters long. If we cut that exact ribbon into 3 perfectly equal pieces, the length of just one of those pieces is simply r divided by 3. Or, written as a fraction, r over 3. We can even track dynamic changes over time using basic subtraction and addition. It's kind of like following a story. Step 1. A bowl contains A apples. Step 2. A boy named Azad gives away 2 of those apples. So our expression for the apples left in the bowl is simply A minus 2. But wait, the story continues. Step 3. Azad receives 7 more apples to toss into his bowl. Now, ignoring the ones he gave away earlier, the new total of apples becomes A plus 7. We're literally just following the events as they happen and adjusting our handy placeholder along the way. Okay, section 3, translating words to algebra. If we use the letter T to represent, say, your age today, we can translate these weird time-traveling sentences directly into algebra. It's basically a simple matching game. The phrase 7 years ago obviously requires us to go backward in time, so we subtract 7 from today's age. That gives us the expression t minus 7. 3 years later pushes us into the future, so we add to our age, making it t plus 3. If someone is twice today's age, we multiply by 2, right? So that's 2t, and half today's age is just t divided by 2. Once you start seeing this pattern, it honestly becomes second nature. Let's do some rapid-fire practice translations to really lock these rules in. Let's see how well we can decode these. Add it to 9 simply becomes 9 plus a. Subtract b from 10 translates cleanly into 10 minus b. Multiply c by 7, that's just 7c. And divide d by 8 becomes d over 8. Now, pay attention to how a slightly more complex, multi-step instruction like subtract 12 from twice of e gracefully translates. First, we figure out twice of e, which is 2e, and then we just subtract 12 from that. Boom, 2e minus 12. Or, check this one out. Divide the sum of 11 and g by 9. We group that sum first, writing 11 plus g, and then put that entire expression over 9. You see, these aren't just random meaningless symbols. They are direct, highly logical translations of human language straight into the language of math. All right, the final stretch, section 4, solving real-world problems. The absolute most crucial point here is breaking the problem down piece by piece. Seriously, never try to solve the whole thing at once. Step 1, we start with an unknown number of p cookies in a single container. Step 2, we need to scale this up to 5 containers. So naturally, we multiply by 5, giving us a total of 5 p cookies. Step 3. Now we're told to take all the cookies from those 5 containers and put them equally into 12 different bowls. So we take our total amount, 5p, and divide it by 12. Our final algebraic expression, 5p over 12. By just taking it one step at a time, what sounds like a giant, complicated word problem becomes a completely manageable mathematical fraction. Let's map out a really complex car park scenario based entirely on just one variable, Q motorcycles. Walk through this with me. Row 1 sets our base. We just have Q motorcycles. Row 2 tells us there are 10 times as many cars as motorcycles, so that instantly translates to 10Q. Now, row 3 is where it gets a little tricky. The rule says motorcycles are 3 times the number of scooters. And hey, everyone makes mistakes in math. Actually, I completely messed up the scooter calculation myself when I first read this. But double-checking the logic showed that if motorcycles equal 3 times the scooters, we have to work backwards to isolate the scooters. So the number of scooters must simply be our motorcycle variable Q divided by 3. Finally, row 4. There are 51 fewer vans than motorcycles, which gives us the easy expression, Q minus 51. Awesome work, powering through those progressive building blocks with me. I mean, look at how far we've come today. We've defined variables, we've identified unknown quantities out in the wild, we've written our very own algebraic expressions, we successfully used letters to represent addition, subtraction, multiplication, and division, and finally, we solved multi-step word problems without even breaking a sweat. It just goes to show that unknown quantities aren't scary mysteries, they're really just simple placeholders patiently waiting for their operations.
Thanks for watching. Bye, students. Don't forget to subscribe for more math fun videos. See you in the next lesson.